Okay, hello, welcome back. So now that we have talked about Newton's equations of motion, it is, I think, a good idea to go over a few details to make sure we are all on the same page and we are not missing any important information. The first thing I want to draw your attention to is the fact that force is a vector. So similarly, when we were talking about positions, velocities, and acceleration, we saw that all these kinematic quantities are vectors. To properly describe, for instance, the velocity of a particle, you need to tell me or anybody how fast a particle is moving and the direction the particle is moving. So both the magnitude and direction were important when describing these kinematic variables. Similarly, force is a quantity that needs to be described and treated with in its vector form. So when you have a force has certain direction and certain magnitude. So for instance, you're pulling a particle, an object, with 10 newtons, whatever the unit, and in a particular direction. If you change the direction of the force, the motions you're causing will be different. As before, we can describe F with a variable with a little arrow on top to mention that it is a force. And when we are talking about net force or imbalance of force, we essentially need to find the summation of all these force vectors. So if, for instance, this one is force 1, you are applying a different force, F2, to the particle. To find the net force, you need to do vector summation. And there are different ways you can do it in algebraic form, for if you know the components of the force in different directions. Or here I want to use just a graphical representation to show that this net force is the vector sum of the forces that we have. And noting that, let's call this F net. Is this. It is, I think, important to reiterate that the magnitude of this total force is not equal to magnitudes of the two forces added together. In fact, from looking at the triangles, with this triangle that is made by the summation, it is actually always F net, the magnitude of net is less than the summation of the two. All right, so that's one thing I wanted to mention. Another thing is when you are solving the equations of motion for your system, let's call it this way, you need to be sure that you are looking at your system or particle in the right way. And you're not missing any force that is potentially contributing to motion. Oops. Make it bigger, this here. Okay. So in the Newton's second law, we saw that sum of forces equals mass times acceleration of the particle. And now we'll see it in a vector form. And when you're trying to find the net force acting on a particle that possibly stays within the system, the first step is to work your way and draw something we call free free body diagram. Or sometimes because I'm lazy, I do this free body diagram. But that doesn't mean it. This acronym really doesn't matter. And what free body diagram means is when you have, I don't know, a bunch of things attached to each other, a bunch of parts. This could be anything, human limbs, a robotic system, systems in a car, and so on. You really need to isolate. Let's try to. What is the best way to draw it? Let me copy it. Can I copy? Copy. Paste. Good. Go away. Go here. Go there. Okay. And there were a whole lot of forces acting on this system. What you really need to worry about is isolating a part and putting all these forces that are acting on the system. Let me change the color. Including the reaction forces that individual bodies are applying to each other. And once you have isolated just one body, you can go ahead and write the Newton's second law for this system. So it is very important, and it helps a lot to draw these forces, making sure that all forces are considered, accounted for, including possible reaction forces between bodies. And then you write the summations of forces and try to relate that to the acceleration of the particle. That is that. We will see a lot more example of this in class. What else? Another thing I want to be very explicit and warn you is the topic of inertia frame. All right, I'm going to score this one so that you know this was the topic. So we have the equation, Newton's second law, sum of forces equals mass times acceleration. Acceleration, we saw when we were talking about kinematics, is related to an observer. So if you have an observer that is moving, they can measure and see a different acceleration. The question is, which observer? How the acceleration should be described or measured? And the answer is, in order to have this relationship, the acceleration must be measured in inertia frame. A frame, an observer that is not moving. Not moving. And a better word actually is, instead of not moving, not accelerating. Accelerating. So as long as your observer is not accelerating, again, that acceleration must be relative to an inertia frame. The measured acceleration that you can use in the equation of motion is valid. To maybe make a case or give examples of when this equation breaks if you are not in an inertia frame. Assume you are an observer looking at another person sitting or standing on a scale, and you are in an elevator. What you see is always a stationary person. So from your point of view, acceleration is always 0. The person standing on the scale, or the scale shows that there is some force acting on the person. So if this is you, or no, this is the person, gravity is pulling the person down, and the reaction of it that is measured by the scale is from the scale to the person. So action and reaction, Newton's third law. And this is the free body diagram of the person. This one is what measured by the scale. Now, if the elevator is not moving, everything is nice, the force of gravity equals the reaction force, and what you really measure is the weight of the person. But you have noticed if the elevator now starts to accelerate, for instance upward, you still observe no acceleration because you are moving with the person. You're looking dead in the eye of the person. You see no motion. But you know that the force that the observer measures, the weight the scale measures increases. So weight measured increases. How do you see this discrepancy? Your free body diagram still looks the same. The weight of the person hopefully stays the same. The acceleration is the same. Oh, don't do that. But another force increase. There is a discrepancy between your equations and what you actually see. And the discrepancy is caused by the inaccurately observed inner acceleration. Because you as the observer have some acceleration, what you measure is a relative acceleration, not an absolute acceleration or acceleration in an inertial frame, and that causes this discrepancy in your equation. You can even take this to the furthest extreme. You can consider a person floating in free space in a satellite, for instance. If you are floating with that person, again, you observe no acceleration, and following the same logic, you conclude that weight of the person is 0, which is inaccurate. There is still gravity acting on the person. The person has a mass in a gravitational field, so the person still has a mass, but this weight is essentially balanced out by the acceleration of you moving with this person. So you have an acceleration. You remember we had this centripetal acceleration, and because you as the observer have some acceleration, you end up with the kind of wrong assumption that the person is weightless. So long story short, for this equation to really work well, you need to measure accelerations in the inertial frame. And maybe last thing I I just remembered that I didn't discuss this in the last video. It's a good place. Unit of force in the SI, the international unit, is in newtons, or in the other systems usually pound is used, and unit of mass is kilograms, or in other units sometimes pound, but pound mass. This is pound force, this is pound mass, or slug, or there are other units. And 1 Newton equals 1 kilogram times 1 meters per second squared. So I think that is all good for now. I have a couple of short description of other forces, and we should be good to close this section.